Inside a sealed cabinet in Houston sits a darkness older than Earth. The largest pieces are barely a centimeter across. The entire treasure weighs about as much as a small apple. Yet hidden in that handful of black dust are salts left by vanished water, carbon-rich compounds assembled before our planet existed, and chemical pieces that life would later learn to use. Some of those pieces were invisible to the spacecraft that traveled billions of miles to collect them. Others were not recognized until years after the capsule came home. That is the real mystery behind the OSIRIS-REx sample from asteroid Bennu. It is not a story about a secret announcement NASA refuses to make. It is a story about a sample so carefully protected, so scientifically rich, and so deliberately saved for the future that nobody on Earth can honestly claim to know everything inside it yet. Stay with me, because we are going to open that story layer by layer. The dangerous touch on Bennu, the stubborn screws in a nitrogen glove box, the ingredients linked to RNA, the evidence for an ancient brine, and the reason most of the sample has not been analyzed at all. If you value calm space stories where the evidence is more powerful than the rumor, subscribe and come with us. This matters because Bennu is not merely a loose pile of rock passing through our neighborhood. Its material preserves chemistry from the beginning of the solar system, before oceans covered Earth and before life rewrote the chemical record. Learning what was possible inside Bennu's lost parent body helps us ask a larger question. Were the raw materials for life rare, or were they scattered across the young solar system? For the beginning, we have to go back to a small world that looked simple from Earth and became stranger every time we moved closer. Bennu is roughly half a kilometer wide at its equator, only a little wider than the height of the Empire State Building. It turns once every 4.3 hours, completing more than 5 days in the time Earth completes one. The asteroid itself probably assembled from rubble 1 or 2 billion years ago after a collision shattered a much larger carbon-rich body, but many of the minerals and organic compounds carried by that rubble trace back close to 4.6 billion years, to the raw material from which the planets formed. That combination made Bennu an extraordinary target. It was primitive, carbon-rich, reachable by spacecraft, and classified as a near-Earth asteroid. It also crossed Earth's orbital neighborhood often enough to matter for planetary defense. A mission could study ancient chemistry and improve predictions of a future asteroid's path. With the same journey, OSIRIS-REx launched on September 8, 2016. The name compressed its goals into a long acronym: Origins, Spectral Interpretation, Resource Identification, Security, and Regolith Exploration. The spacecraft left Earth, returned for a gravity assist in September 2017, and tilted its path to match Bennu's orbit. It reached the asteroid on December 3, 2018, after traveling through interplanetary space for more than 2 years. The first close images immediately disrupted the plan. Telescope observations had suggested areas of fine, relatively smooth material. The actual surface was a field of jagged boulders, some as large as a 6-story building. Choosing a sampling site was like searching for a clean parking space in a landscape made almost entirely of broken concrete, except the parking vehicle was operating hundreds of millions of kilometers from its drivers. The team selected a small site called Nightingale inside a northern crater about 140 meters wide, roughly the length of 1.5 football fields. To reach it safely, the spacecraft used images of the surface to compare what its cameras saw with stored maps. If it drifted toward a dangerous boulder, it could cancel the descent on its own. That autonomy turned a spacecraft designed for a broad landing zone into one capable of touching a much tighter target. Even orbiting Bennu required a different intuition from orbiting a planet. Its gravity is about 100,000th of Earth's, so weak that sunlight warming the spacecraft and tiny releases of heat had to be considered in navigation. At the end of 2018, OSIRIS-REx entered an orbit with a radius measured in little more than a kilometer. At the time, Bennu became the smallest body ever orbited by a spacecraft, and the orbit itself was closer to the scale of a neighborhood walk than a journey around a world. Then Bennu began throwing stones. Navigation images revealed hundreds of particle ejection events. Some fragments escaped, some briefly circled the asteroid, and most fell back. The activity was not the violent eruption of a comet. Possible causes included thermal cracking, impacts by tiny meteoroids, and water released from minerals, with more than one process potentially involved. But the discovery changed the safety picture and offered a living view of how rubble pile asteroids lose and rearrange material. Global mapping also confirmed hydrated minerals across the surface, showing that Bennu's ingredients had once interacted with water. Yet the maps could not reveal how many different chemical environments were folded into the rubble. For that, a Gramenal laboratory would be worth more than another global picture. The mission still had to obtain it. On October 20, 2020, the spacecraft descended with its sampling arm extended. The circular collector at the end was the only part intended to touch Bennu. Contact lasted about 6 seconds, shorter than a slow breath. 1 second after contact, a bottle released nitrogen gas into the surface. The burst lifted dust and pebbles into the collector while the spacecraft prepared to back away. The surface did not behave like firm ground. The sampling head sank about 49 centimeters, nearly knee-deep, as weakly bound particles moved around it. Later analysis showed that without the immediate reverse thrust, the spacecraft could have continued sinking into Bennu like a person stepping into a children's ball pit. A world that looked covered in solid boulders was, at the local scale, astonishingly fragile. Images taken afterward showed another problem. The collector was so full that larger particles appeared to hold its thin flap partly open. Small pieces were escaping into space. The team canceled a planned measurement of the collected mass and moved quickly to stow the sampler inside the returned capsule. Too much success had created a new risk. The spacecraft left Bennu on May 10, 2021, after a 7-minute engine burn pushed it away at nearly 1,000 kilometers per hour, comparable to a passenger jet. It then spent about 2.5 years looping back toward Earth. By the end of the primary mission, the round trip had covered roughly 3.5 billion kilometers, a distance equal to thousands of journeys from Earth to the Moon and back. On September 24, 2023, OSIRIS-REx released the sample capsule about 102,000 kilometers above Earth, roughly a quarter of the distance to the Moon. The capsule entered the atmosphere, deployed its parachutes, and touched the Utah desert at about 18 kilometers per hour, close to the speed of a person. Jogging, within 70 minutes, recovery teams had wrapped it for transport. The carrier spacecraft never landed. It diverted past Earth and began a new mission toward the asteroid Apophis. The capsule went to a laboratory built to keep earthly air, moisture, dust, and biology away from Bennu's material. Nitrogen surrounded the sample because it is far less reactive than ordinary air. That protection is not a cosmetic detail. If researchers find an amino acid or sugar, they must be able to argue that it came from the asteroid rather than a fingerprint, a drop of water, or a microbe from Earth. Now, here's something that surprises a lot of people when they first hear it. The first material scientists saw was not even the main sample. Black dust and small rocks coated parts of the canister and the outside of the collector head. This bonus material alone pushed the accessible amount beyond the mission's minimum requirement of 60 grams, about the mass of a large chicken egg. The main chamber still held more. Then 2 of the collector's 35 fasteners refused to move with the tools approved for the glove box. The team paused rather than forced them. New tools had to be designed, manufactured, tested, and proven safe around the pristine sample. In January 2024, the fasteners finally came free. When the remaining material was poured into trays, the complete returned mass reached 121.6 grams, more than twice the mission requirement and the largest asteroid sample ever collected in space. The delay fueled dramatic headlines, but the explanation was public and practical. The obstacle was not a locked secret. It was contamination control. A normal steel tool could introduce material that would confuse later measurements, so the solution had to work inside a restricted nitrogen environment and preserve the scientific value of grains smaller than sand. The first broad analyses showed a carbon and nitrogen-rich sample dominated by hydrated clay minerals. Hydrated does not mean Bennu contains liquid water today. Bennu has no meaningful atmosphere, and its present surface swings between temperature extremes that cannot sustain an ocean. The clay's record water-rock reactions on the much larger parent body from which Bennu's rubble eventually came. Researchers also found carbonates, iron oxides, iron sulfides, magnetite, and an unusually pure magnesium-sodium phosphate. That phosphate was especially striking because the spacecraft's remote instruments had not identified it at Bennu. A spectrometer looking at sunlight reflected from the surface can reveal a great deal, but it probes only a thin optical layer and averages signals across mixed materials. In a laboratory, scientists can isolate a particle, cut it, scan it, dissolve part of it, or examine structures smaller than a human hair. Now stop and sit with that for a second. A spacecraft can map an entire asteroid and still miss a mineral sitting inside the sample it brings home. Returning the material does not merely confirm remote observations, it changes the scale of the question. The phosphate mattered for another reason. On Earth, phosphates participate in energy transfer, cell membranes, and the backbones of genetic molecules. Finding phosphate is not finding life, and the script must keep that boundary bright. But its purity and grain size, together with water-altered clays, suggested that Bennu's parent body once hosted a more complicated watery environment than a simple damp rock. That suggestion sharpened in January 2025. Scientists reported a sequence of sodium-rich minerals formed as briny water evaporated. Think of a shrinking salt lake leaving different crystals behind as the water chemistry changes. The Bennu sample preserved a comparable mineral progression on a microscopic scale, including delicate salts that are difficult to recognize in meteorites after uncontrolled exposure to Earth's atmosphere and water. The sequence implied that liquid on the parent body did not appear for a moment and vanish. Water may have circulated and concentrated dissolved chemicals over an extended period, possibly thousands of years or longer. The parent world was not Earth-like, and no evidence shows an inhabited ocean. A better mental picture is a small, primitive body warmed from within, where melted ice reacted with rock and then retreated into increasingly salty pockets. As those pockets shrank, different dissolved substances would reach saturation at different times, crystallizing in an order that preserves the changing brine. Researchers identified a suite that included carbonates, phosphates, sulfates, chlorides, and fluorides. Some of these minerals are so water-soluble that rain or groundwater can erase them from meteorites after arrival on Earth. The controlled return therefore preserved not only what the parent body made, but relationships between minerals that ordinary delivery through the atmosphere can scramble. The scale of the inferred liquid environment also requires care. Bennu itself is too small to have maintained that ancient reservoir. The reactions happened within its larger ancestral body before a catastrophic collision broke that world apart. Bennu is a later rubble pile, assembled from fragments of a place that no longer exists. Each grain can therefore be both a piece of the asteroid we visited and a sample of a much older lost world. And this is where the story gets stranger. The same sample carried both the mineral record of that brine and a broad inventory of organic chemistry.